Hello, my name is Jonne Kleyheeg Hartman. I am a senior bird ecologist at Bureau Waardenburg, one of the bigger ecological consultancies in Europe. At Bureau Waardenburg, we have more than 20 years of experience in ecological studies related to wind energy, both onshore and offshore. Besides monitoring ecological effects, such as collisions and avoidance, and how to mitigate these effects, we are also keen to look into opportunities for nature within wind farms. For more information, we kindly invite you to have a look at our other presentations or visit our website. In this presentation, I will focus on mitigating collision mortality of nocturnally migrating birds with radar-controlled shutdown. Our project location, the Eemshaven, is a harbour area that is located in the northeastern tip of the Netherlands in the province of Groningen. The Eemshaven region currently accommodates almost 100 wind turbines, shown with red dots on this map. There are plans to install another 100 wind turbines in the blue shaded areas in the coming years. The Netherlands are on a key position in the East Atlantic Flyway, with the Wadden Sea being a very important staging area for migrating birds. Every year, huge amounts of birds that migrate between southern and western Africa and Western Europe and the Arctic travel over the Netherlands. Due to the geographical position of the Eemshaven at the coast of the Wadden Sea, each spring and autumn hundreds of thousands of birds migrate over this area, of which many migrate during the night. This combination of many wind turbines and many migrating birds leads to a large number of collision victims of migrating birds each year. From a monitoring study in the existing wind farm, we know that at every wind turbine in the Eemshaven area, on average 33 birds are killed each year, of which almost half are migrating songbirds. The province of Groningen is seeking ways to reduce the number of collision victims of migrating birds. One way to do that is to shut down wind turbines in periods of high collision risk. To prevent problems in the electricity grid, the moments of shutdown of the entire wind farm have to be predicted at least 48 hours ahead. Therefore, the province of Groningen, together with several Dutch ministries, asked a research consortium to study the feasibility of the development of a predictive model for shutdown on demand. The research consortium consists of 3 parties: Bureau Waardenburg, the University of Amsterdam, and another Dutch ecological consultancy called Altenburg and Wiemega. The project covered 2 migration seasons, autumn 2018 and spring 2019. In these 2 migration seasons, Bureau Waardenburg measured local patterns in bird migration with a novel 3D bird radar in the Eemshaven. The University of Amsterdam worked with the data of the weather radar at the island of Borkum in Germany, approximately 15 kilometers north of the Eemshaven. Altenburg and Wiemega has performed collision victim searches under 20 to 30 wind turbines in the Eemshaven in the period that migration patterns were measured by radar. The University of Amsterdam is planning to use historical data of weather radars in the vicinity of the Eemshaven for the development of the predictive model for shutdown on demand. However, weather radars look over a large distance of several tens of kilometers and at large altitudes up to 4 kilometers, but not below 100 meters. To check whether the data of these weather radars can be used to determine the occurrence of strong migration at rotor height in the Eemshaven, we compared the data of the weather radar at Borkum with the data of the 3D bird radar in the Eemshaven. Additionally, the fluxes at rotor height resulting from the radar measurements were used in a collision rate model to obtain an estimated mortality. We compared this estimated mortality with the estimated mortality resulting from the corrected field counts to obtain information on avoidance rates. The idea is that the collision rate model eventually can be used to estimate the number of casualties that can be prevented by the shutdown measure. In this presentation, I will focus on the part of the project that is highlighted on this slide, in which we studied the feasibility of the development of a predictive bird migration model for rotor height based on weather radar data. But I do not want to keep all results of the field counts of fatalities from you, so I will start by showing the main results of that part of the project. The mortality of nocturnally migrating passerines was lower in spring compared to autumn. The species that was most often found as collision victim was the goldcrest, with 14 fatalities in autumn and 2 more in spring. When we extrapolate the results in a simplified way to the entire wind farm, over 1,000 nocturnally migrating passerines are killed in wind farm Eemshaven in autumn and over 500 more in spring. This means that the mortality of migrating songbirds in this wind farm is even slightly higher than expected based on the results from the earlier collision monitoring that was originally designed for bigger bird species. Simultaneously with the field counts of fatalities, we measured local migration intensity and flight behavior of birds using the innovative 3D bird radar called MAX, manufactured by Robin Radar Systems. MAX was located in the western part of the Eemshaven. Its position is marked with a star on the map. The most important innovative feature of this radar is that it automatically records the flight path of every bird within its reach in 3D and stores it in a database. This gives us loads of new possibilities for the study of behavior in and around wind farms, like for instance the study of avoidance on a macro or meso scale. With the tracking and classification software, birds can automatically be followed and information on the approximate size of the bird is given. Species recognition is not yet possible. Field ecologists are still needed to add species information to the recorded tracks. This graph shows the average migration intensity per night for the 2 studied migration periods. We found some profound differences between autumn and spring migration. In autumn, migration was much more peaked compared to spring. Additionally, in autumn both the average as well as the maximum nocturnal migration traffic rate was higher than in spring. Part of the explanation is the presence of much more young birds in autumn. Another explanation is that in spring birds take different, more direct routes, which means that less birds are following the coastlines. Migration appeared to occur at very low heights in the Eemshaven, with most birds below rotor height, but also lots of birds at rotor height, approximately 37% in autumn. There were hardly any differences between autumn and spring in the altitude profile. A comparison of the timelines of MAX and the weather radar at Borkum, in this case for approximately 2 weeks in October, shows that the timing of nights with intense migration strongly overlaps. As the weather radar looks at much larger heights than the 3D bird radar, in some nights the peak measured with the weather radar is larger than measured with MAX, such as in some nights at the end of October. In these nights, relatively more birds seem to fly at higher altitudes. This figure that I am going to show you now step by step is basically the wrap-up of the feasibility study. The figure is based on the measurements that were performed in autumn 2018. As both the overall migration intensity and the number of nights with peak migration were higher in autumn, shutdown of the wind turbines to prevent collisions of nocturnally migrating birds would have been most effective in this period. In the upper figure with the blue bars, you see the cumulative migration intensity at rotor height and per night that was measured with the 3D bird radar MAX in the Eemshaven. The black bars in the figure below that show the cumulative migration intensity per night that was measured with the weather radar at Borkum at higher altitudes. You can see that there is a good match in the timing of nights with peak migration. The red bars in the bottom figure on the left shows the migration intensity that was predicted by the FlySafe model. This model was developed approximately 10 years ago for altitudes above rotor height, and it provides near real-time information and forecast on large-scale bird movement in the airspace of the Netherlands, Germany and Belgium. This information is used by the Belgian Air Force, the Royal Netherlands Air Force and the German Bundeswehr to warn their pilots, enabling them to adjust their operations and avoid collisions between aircrafts and birds. The predictions of this model do not match very well with the measured migration intensities with the two radars in the Eemshaven region. Now let us take a look at the figure on the right. The y-axis shows the percentage of the flux that was measured in autumn 2018 and the x-axis shows the number of nights. To create the three lines, we arranged the nights according to the measurements of the 3D bird radar shown in the upper left figure in blue, starting with the night in which the highest cumulative migration intensity at rotor height was measured. So the first night, based on the max measurements, is the one depicted with the arrow. In this case, it was the night from the 10th onto the 11th of October. For all three lines, the corresponding percentage of the entire measured or predicted autumn flux is shown for the first night in the figure on the right. Because the black line, based on the measurements of the weather radar, is very close to the blue line, based on the max data, we can conclude that it is possible to build a predictive model for migration intensity at rotor height based on weather radar data. This model has the potential to be better than the existing FlySafe model for higher altitudes, as is shown by the distance between the red line and the black line. We found that each year more than 1,500 nocturnally migrating passerines are killed in the existing wind farm in the Eemshaven. The radar data showed that autumn migration is more intense and more peaked than spring migration. Thanks to the local 3D bird radar, we know that in the Eemshaven, migration doesn't only take place at higher altitudes and that a significant part of the birds flies at rotor height. The most important conclusion of the study is that it is possible to develop a predictive model for passerine migration at rotor height based on weather radar data. The logical first step after this feasibility study is to develop the predictive model for nocturnal bird migration at rotor height for the Eemshaven region. To use this model for mitigation purposes, we have to decide on appropriate thresholds for shutdown of the wind farm. An obvious threshold is the predicted migration intensity at rotor height. However, it is also possible to take into account the production loss to minimize the economic impact of mitigation. This would lead to more or longer moments of shutdown, but with a lower resulting production loss. Additionally, it would be good to also incorporate a collision rate model in the management of the shutdown, with which the predicted migration intensity can be translated into the expected number of fatalities. To be able to do this in a proper way, we need more information on the local conditions under which most collisions occur. To obtain that kind of information, dedicated field counts of fatalities based on a very high search intensity are needed. In the end, there is a clear wish to expand the applicability of a predictive model for shutdown to prevent collisions of migrating birds to other regions in the Netherlands and preferably, if possible, to the entire country. For a quick and entertaining wrap-up of this project, please enjoy the comic on the left. I would like to thank you very much for watching this presentation. Do not hesitate to contact me if you have any questions or suggestions. As a close, I would also like to point your attention to the conference on wind energy and wildlife impacts that we are organizing in the Netherlands in April 2022.
I would like to ask you, in your opinion, what are the implications for the use of radar technology in sensitivity mapping?
Thank you. Good question. At Bureau Waardenburg, where I work, we use radar a lot actually for sensitivity mapping. What it can give you is a long-term insight in spatial and temporal patterns in flight activity of birds. And especially with the new 3D radar, this information is not only on the horizontal scale, but it is also on the vertical scale. So you get very detailed information on flight activity at rotor height for a specific area. And especially if you'd like to know in the planning phase of a wind farm, if there are specific positions where wind turbines are a good idea or are maybe in a wrong position because there is a lot of flight activity at rotor height, then radar gives you very useful information and also a lot of data, way more data than what can be gathered visually. What we usually do is we make a combination of radar observations with visual observations, because the limitation of radar is that you won't get species-specific information. And for most wind farms, there are specific species of interest that you want to know more about. So then we use radar to get information for a large area and a lot of data, and also detailed data about the position of flight activity of birds. And then we use visual observations to add information on species and bird numbers.